This Zoom session is being brought to you by the Fractal Horizon Forming. All right, for today, we'll be doing sections 3.3 and 3.4 about solving linear systems. Uh, all right, fine. Oh, actually, it's solving 3x3 linear systems. A 3x3 linear systems has three equations in three unknowns. And ax plus by plus cz equals j, dx plus ey plus fz equals k, gx plus hy plus iz equals l. A through L are constants, x, y, and z are the variables we're trying to solve for. Okay. We will solve a system like this, like the way we solve 2x2 systems, by row operations. Given an equation, we can rescale it. So a equals b becomes ka equals kb. And we can combine equations. We can, to the equation a equals b, we can add k of c equals d, and let's get a plus kc equals b plus kd. We solve by elimination by using row operations to eliminate variables. All right, now here we start off with, here are two cases of checking a solution of a system. 2, 1, 1, does it solve x minus y plus z equals 2, 2x plus y minus z equals 4, 2x minus 3y plus z equals 2? Well, plug in 2 in for x through these, 1 for y for these, 1 for z for these. So first equation becomes 2 minus 1 plus 1. It does indeed equal 2. Check. Plug in for the second equation, twice 2 plus 1 minus 1 does indeed equal 4. Check. 2, 1, 1 in for this. 2 times 3 minus 3 times 1 plus 1. That's 4 minus 3 plus 1. Does indeed equal 2. So check. So this number triple does indeed solve this linear system. Now here's 6, negative 5, 7, negative 5. Does it solve this system? 3x minus 2y plus z equals 37. X plus 3y minus 3y equals 27. 2x plus 7y plus 2z equals negative 48. All right, long story short, you plug it at 6, negative 7, negative 5 into the first equation, and it checks. You plug 6, negative 7, negative 5 into the second equation, and again it checks. But if you plug into the third equation, 2 times 6 plus 7 times negative 7 plus 2 times negative 5, you get 47, which does not equal 48. So it does not fit the third equation, and therefore this does not fit the system. The number triple has to fit all three equations. Now, here we go. Here we go about solving a system. Solving a 3x3 system is like twice as hard, or at least takes twice as many steps. Well, a little bit more than a 2x2, because there are just so many more variables and numbers to deal with. What we do, here we have x plus y plus z equals 2, 2x plus y minus z equals 1, 2x minus 3y plus z equals 1. What we'll do is we'll pivot on entries. So here's this x right here. This is a 1 of this x. We'll use this and combine it with this and this equation to eliminate these two x's. Here's a 2x. Well, we needed to subtract twice equation 1 to eliminate this 2x. We'll eliminate this 2x again by subtracting twice equation 1 from it. So here's what we get. So x plus y plus z equals 4 remains. Now, 2x minus twice x cancels. Y minus twice y is negative y, so we put a negative y there. Negative z minus twice z is negative 3z, so we put a negative 3 here. And 1 minus twice 4 is a negative 7, so we put a negative 7 there. Now for this one, 2x minus 2x cancels. Minus 3y minus twice y is minus 5y, so we put a minus 5y there. Minus 3y minus twice, z minus twice z is negative z, so we put a negative z there. And 1 minus twice 4 is a negative 7, so we put a negative 7 there. All right, so we've eliminated x from all but the first equation, so we're sort of a third way along. Now, all right, both these equations have negative signs. We'll get rid of them by multiplying them throughout by -1, rescaling by -1. And so this becomes this becomes this. X plus y plus z equals 4. Y plus 3z is 7. 5y plus z is 7. Now, I pivot on this y here. We'll use this y here to eliminate this y in the first equation and this 5y in the third equation, excuse me. Here's how we do this. We eliminate this by subtracting equation 2. We eliminate this 5y by subtracting 5 times equation 2. And so y minus, so we wind up with, we keep y plus 3z equals 7 in there. Okay. And y minus y cancels, so 0. Z minus 3z is negative 2z, so put in negative 2z here. And 4 minus 7 is a negative 3, so we put a negative 3 there. For this, 5y minus 5y cancels, 0. Excuse me. Z minus 5 times 3z is negative 14z, so we put a negative 14z there. 7 minus 5 times 7 is a negative 28, so put a negative 28 there. Now we have this system. As you can see, it's starting to get a little sparse, which is good. This last equation, negative 14z equals negative 28, well, we can solve by dividing throughout by negative 14, and we get z equals 2. And the other equations remain. X minus 2z equals 3, negative 3, y plus 3z equals 7 from here. Z equals 2. Now we'll pivot on this z to eliminate this 3z and this minus 2z. We'll eliminate the minus 2z by adding twice equation 3. We'll eliminate this 3z by subtracting 3 times equation 3. All right, now since there's nothing happening here, these parts stay the same, so x remains the same. Negative 2z plus twice z is 0, poof. Negative 3z plus twice 2 is 1, so we get a 1 there. Here 3z minus 3 times z cancels, poof. 7 minus 3 times 2 is a 1, so we put a 1 there. And we're done. X is 1, y is 1, z is 2, and there's the solution to the system. So to recap, we use row operations, specifically combining, to pivot on entries. We use this entry, this x here, to eliminate these x's here, like that. Then we do some rescaling and to make things neaten things up a bit. Here we pivot on this y here to eliminate this y and this. We get this system here. Here we rescale to get a specific value of z, z equals 2. Then we pivot on this z to eliminate this and this, and we get this. X equals 1, y equals 1, z equals 2. Well, here we'll go with this. 7a plus 9b minus 2c equals negative 5. 5a plus 14b minus c equals negative 11. 2a minus 5b minus c equals 3. In this case, I rescale this by a negative 1 to get a negative 2a plus 5b plus c equals negative 3. Now I'll pivot on this entry, this c here, to eliminate this c here and this minus 2c here. We do that by adding twice equation 3 to equation 1, by adding equation 3 to equation 2. And okay, after a large amount of arithmetic, we get this system here. 3a plus 19b equals negative 11. 3a plus 19b equals negative 14. And this remains 2 minus 2a plus 5b plus c is negative 3. I think you can already see the trouble's coming, because here 3a plus 19b is trying to be two different numbers at once. I can't do that. We can see that if we take this equation and subtract equation 2 from it. Then the 3a's cancel, the 19b's cancel, and negative 11 minus negative 14 is 3. And so you get the equation 0 equals 3, which is not true. Otherwise, I'd have $3 in my pocket right now. So since it's not true, the original system can't be true, and there is no solution to the original system. If we ever get non-zero equals 0, there's no solution. Here's a very similar one. Okay, here this is kind of messy. 2x plus 3y equals 6 minus 4z. 2x equals 3y plus 4z minus 4. 4x plus 6y plus 8z equals 12. Okay, a mess because there's variables on both sides of both these equations. So we do some transposing. Move this left, move these left. Here we go. 2x plus 3y plus 4z equals 6. 2x minus 3y minus 4z is negative 4. 4x plus 6y plus 8z equals 12. All right, fine. Well, all right, after some row operations like removing a factor of 2 from here, and then, oops, notice this. This equation is the exact same as this equation. There's some redundancy. And when we subtract equation 3 from equation 1, you get 0 equals 0, which is true, but also uninformative. So when you have that, in effect, we have only 2 equations worth of information to find 3 variables, and that's not enough. So we get we get mini solutions. It's what's called underdetermined. There's not enough information to specify. So you get no solution, aka overdetermined, if you get non-zero equals 0, like 0 equals 3. If one of the equations cancels out entirely, for 0 equals 0, then it's underdetermined. There'll generally be more than one solution, or in fact, a whole line full of solutions or more. Okay, that's it for now. So let's stop the